Well, welcome back to our discussion of neural networks. We were just getting into how we can create an artificial neuron, the different elements. And so we have the mathematical constructs here. And then we are then getting into this log sigmoid or tan sigmoid type of function. And so just to give you a perspective of where this is both of these things have a thresholding function that are shown here in this figure. And so this is what we're just finished up at the last part of our first segment. And now we're getting into it in more detail. So we have these mathematical functions for these activation function. First, the log sigmoid, and second, the tan sigmoid that we can have. So two different models there. And now let's talk about the feed forward type of networks. This is what a two-layer network would look like. A feed forward network consists of a set of input terminals with feed the input patterns to a layer, a subgroup of neurons. The layer of neurons make independent computations on data that it receives and passes the results to another layer. The next layer may in turn make its independent computation and pass it on the result to yet another layer. Finally, a subgroup of one or more neurons determines the output from the network. And so this is where we can see we had this model before. So this would be showing you an example of one neuron there. And that information can be fed on to some more processing as we go on. Feed-forward networks are the most commonly used network architecture since it works quite well in many practical applications. So we have the input terminals defined here as X, and the hidden layer output ZL may be represented with the equation shown here. The weights consist of input terminals to hidden layers. So we have the W values for the weights. The output layer nodes as Y hat Q, we may write with this kind of equation, and the weights connecting the hidden layers to the output are shown here, where VTQ is defined to be that set of parameters that we're listing there, all multiplied together, VQ1, VQ2, all the way to VQM. For the multi-class discrimination problem, one may use two-layer feed-forward neural networks with sigmoid hyperbolic tangent hidden units and sigmoidal output units. The neural network output of this multi-layer structure may be written with this equation that we're showing here. Here is an illustration of a neural unit with a differentiable activation function. And so this is similar to what we saw here, but this function here, it has a slightly different type of characteristic shown with that type of a model for the input to the output, the relationship. So let's talk about the error correction delta rule. A neural unit has a differentiable function sigma A. First, a linear combination of the inputs, which deals with the activation value A, are computed. Then a non-linear activation function, sigma A, is applied to the result. The output, Y hat, of nonlinear unit is a continuous function of its input A. The problem is to find the expression for the learning rule for adapting weights using a training set of pairs of inputs and output patterns. Here is the mathematical details behind some of that, where we're dealing with the error correction delta rule here. First, we were just giving some general insight into that. And so the error function EK may be defined as listed here with the supporting equation Y hat below that. For each training example I, weights Wj and from j equals 1 to n and plus the bias Wo are updated by adding to it the delta Wj and delta Wo. So the learning rule can be written with these two equations. It is also known as the delta learning rule, with the delta defined here. Delta k equals to E k sigma prime A k. In terms of delta k, the weight update equations become here. And interestingly, for a linear activation function, it holds that sigma kx is equal to ak. So we have some more development here. We talk about what this might be for the log sigmoid, and we talked about the log sigmoid at the beginning of this chapter. So keep that in mind. So we'll have a couple more slides here on the error correction delta rule. First of all, let's focus on training protocols. The batch training rule computes the weight updates after the summing the error over all the training examples, that is the batch of the training data. Incremental training rule is to update the weights incrementally following the calculations of errors for each individual example. So here are some examples. First, we have the scalar output MLP network. And here we have the output layer of the vector output MLP network. And so here we can see each one of these is a neuron. And we're seeing we're producing these potential outputs y hat 1 through y hat m. Here we're looking at, we can be summing these various products together to come up with the estimation of y hat. So this is using forward propagation. And this is trying to do error signals on back propagation. So there's a way of having feedback to look at things that way. I definitely would recommend that you read over this information in the textbook. It'll go over this in more detail than what we're trying to capture with this high-level lecture. The weights update equation employing the incremental training for the multi-output structure, the log sigma output units. Forward recursion is used to compute the MLP output. You present the input xi to the MLP network and compute the output using these equations. With the initial weights randomly chosen, back recursion for the back propagated errors, we have these equations that we can be leveraging, and the computation of the MLP weights and bias updates are shown there. So then for error propagation algorithms, the weight update equations employing the batch training for the multiple output structure, the log sigmoid output units, the initial weights are randomly chosen and an iteration index is set to 0. All training data pairs are presented to the network before the algorithm integration index k+1 moves to the update the weights. And the weights update is done using the following equations. And this is just some more details for that for the error propagation algorithms. I'm not going to go through this, but I'll pause there and we'll continue on with just a few last charts for our final part of this lecture.